Welcome everyone. In this video, I'll demonstrate how a database workload looks from the point of view of a disk. So I'll briefly describe what we're looking at. The surface of the screen corresponds to a disk volume. The disk volume is 450 gigabytes in size, and it's divided into 500 horizontal stripes, each about 900 megabytes in size. If you see a random point of light, then it corresponds to random I/O. And if you see a point of light moving from left to right, it corresponds to sequential I/O. And the rate at which it's moving corresponds to the bandwidth that it is consuming. And reads and writes are color-coded, so they'll be distinguishable. The database is ScyllaDB, and the machine is an Amazon i4i.large instance. 1 core, 2 vCPUs, and that 450 gigabytes NVMe disk. So let's start. So the workload starts by writing just to the commit log. The user workload Cassandra stress is writing to the database, and there is no disk activity other than writing to commit log because all of the data is maintained in memory up until now. So now we've just overflowed memory. And the database started to flush its in-memory data structure to disk, to a disk file called an SS table. And we see 2 data files being written, and also we see 2 index files being written. They're written too slow to actually be noticed as a sequential write, but it is still a sequential write. The reason that we see 2 of each is because this is a thread per core design. So each thread is more or less a mini database or a shard acting independently of the other shard. This allows avoiding locking. So we have now writes, we have commit log files being written, and we have data from in-memory data structures from Memtable being dumped to SS tables. And right now, the number of SS tables has become large enough that the database wants to reduce the number of SS tables, so it's beginning to read. And green represents read, and we see that it's reading very slowly. It's almost impossible to notice the rate at which it's reading. And the reason is that the database does not feel any pressure right now. The number of files is still rather small, and so it's only devoting a small fraction of the bandwidth to this compaction process. Here you can see a compaction input. Here you can see a compaction output. And just like with the Memtable flush, a compaction output is actually 2 files. One of them is a data file, and one of them is the index file. And also, here and there, you should see random writes to the file system commit log. It's hard to notice them. They link along here and there. So one feature that can be seen is that the disk area is divided into 4 distinct stripes. So this one here, here, and here. And the reason for that is that the file system, XFS, divides the disk area into 4 allocation groups, each of which is relatively independent. And it does that to avoid lock contention and to simplify its allocation behavior. It will do this depending on the size of the disk and the amount of vCPUs. This is a relatively small disk, so it decided to divide it into just 4 different allocation groups. So I think that the number of compactions that are going on has increased. We can see more green dots representing reads, but the database still is devoting only a very small fraction of the disk bandwidth to the compaction, and most of the bandwidth is going to the commit log. Here we see 2 commit log writes, and to Memtable flushes here and here. The reason I know which one are the commit logs and which one are the Memtable flushes is a quirk of XFS and the database, where XFS will lay out all of the files in a single directory in the same allocation group. So there is and this is the allocation group that corresponds to the commit log file directory. So everything goes here. The SSTable files also go into a single directory, but there we hacked it a little bit by first creating a temporary dummy directory, creating the SSTable file there, and then moving it back. And this way we spread out the writes to use all of the areas of the disk and avoid lock contention. On such a small machine, the lock contention doesn't matter, but on a large machine, it can lead to fragmentation of the allocation group in use and bad performance. We probably should do it for the commit logs as well, but we still haven't. So compaction is still going on. Perhaps I should explain a little bit about how I produced this video. So I used the IO trace point in the Linux kernel. These are just points that they collect data. Normally, they are just NOP instructions. But if you run a program called block trace, written by Axbow, then it will start forwarding all of the IO request parameters to user state, which will write them into files. And there is a program called block parse, which will convert this into a text representation. There are also two software packages that will take this capture and convert it into a movie format, but I did not like the output of those packages, so there are now 3 open source packages that do this. I used Python Pillow to draw each frame, and MoviePy to generate the movie. It's using FFmpeg in the background. Okay, so the write is still ongoing. I think it has maybe half a minute more to run. We can see that it's doing quite a lot of compactions, but still at a low rate compared to the write. If I were to let this run for much longer, then eventually the database would begin to feel the pressure and increase the compaction throughput at the expense of commit log. I think the compaction, the write workload ended, and now the database notices that it has no other activity beyond its compaction, so it speeds up the compaction. Here it zooms off, and it's basically using idle time in order to clear its backlog. It's getting prepared for the read workload, or basically any workload that will come, just using spare CPU and spare bandwidth. At this time, I'm fumbling and looking for the syntax for the read workload, making a lot of typos, but it gives us time to watch the compaction process. And there we just saw a big flash in red color, and that's a discard. So what happened is that the compaction process completed and deleted the input files because they're now represented in the output files. There was another one, so another compaction process completed. And it's telling the disk, so the database told the file system that those files were no longer in use, and the file system tells the disk that these disk areas are no longer in use and can be recycled because the SSD underneath is quite a complicated beast. We now have just 2 compaction processes, so they're both distinctly faster. We have a saying at ScyllaDB that if you're experiencing bad latency, then check the discard setting. If it's enabled, then disable it. And if it's disabled, then enable it, and your problems will be solved. Fortunately, that's now just historical. It's the disks and the file system have improved to the point that it's no longer necessary to play with discard, and we just keep it enabled at all times. There are 2 ways to perform discard. One is online, which is what we see now, that as soon as the file is deleted, the information that it's deleted is forwarded to the disk so that it can recycle the storage. And the other is offline, where you run a process once a week that sends everything to be discarded. And here we see that the read workload is finally started. And it's a random read with a Gaussian distribution. I used Cassandra stress to generate both the writes and the reads, occupying about 50 gigabytes of data, so about 10% of the disk volume. And we can see that the compaction is still ongoing. These are the compaction writes, but the rate is much lower. So previously, the database saw that it had nothing to do, so it pulled all the stops and let compaction proceed quickly. But now it's throttling compaction in order to serve the read workload as fast as it can. It's still letting compaction make some progress. An artifact that we see is that although most of the inputs for compaction are hidden within the noise of the random reads, we still see one or two. Here is one, and here is another one. And these are files that are being compacted, but it seems like there is no read activity around them. And my explanation is that these are likely to be the last SS tables that were dumped as the Memtables. And because of that, they're still in cache. They've not been pushed out yet. And so any records that are stored in those SS tables are served from cache instead of being served from the SS tables. So a nice artifact here. Anyways, this continues for a while. I guess it's nothing very interesting will happen. So let's just skip a little bit closer to the end of this read workload. So a few more seconds left. And the read workload is ended. And of course, the database seizes on the opportunity and starts compacting like crazy in order to utilize this lull to be prepared for the next workload. It doesn't know that I'll terminate it as soon as it's done. Here we saw another compaction ending, and there is just one compaction left, one shard running like crazy, compacting about 10 input files into one. Here we can see the index file, and here we can see file system metadata, the XFS commit log being updated. And there's the last compaction completed. We discarded all the input files, but it was all for naught because I terminated the instance. Let's take a look at something else. Let's take a look at how the database was. Let's take a look at the database perspective of what was happening. So the database is exporting a lot of metrics to a Prometheus database, and now we're viewing it via Grafana. I hope the dark mode doesn't disturb anyone. So let's take a look at commit log. So we saw in the beginning that commit log was running all alone, and so it was able to utilize all of the disk bandwidth. But very quickly, it ran out of memory, and now it has to share the bandwidth with the Memtable flush process, and also with compaction. So it's sharing the bandwidth with the Memtable flush with about 1-to-1 ratio, and compaction is taking a small but steadily increasing share of the bandwidth. So we can see that each shard is doing about 60 megabytes per second, slowly decreasing towards 55, so 110 to 120 total. And if we divide it by the IOPS chart, we will get the average a write size of 128 kilobytes, which is what we determined was good both for achieving good bandwidth without a lot of CPU usage, and also without disturbing the latency. So if you do a larger write, you can get a lower CPU usage per byte, but also you will get latency jitter from those writes because the disk will be busy serving the write and not able to serve the read. And speaking of latency, let's look at the latency chart. And there are actually 4 lines here. The 2 top ones in green and yellow are the queue latencies. I mean, they're quite high, which is understandable because this is an IO-bound workload. We're saturating the disk, so any excess work that the disk is not able to take will just get queued. But what's also interesting is the disk service time, which is in those 2 lower lines, which are almost at 0. If you read the pop-up, it's about 1/4 of a millisecond. And the database is careful to only push as much work to the disk as will occupy it for about 1/4 of a millisecond. And the reason is that this allows it to manage where disk bandwidth gets allocated. So if it just throws a request at the disk, then it's up to the disk to decide which request it will service more quickly. And usually it will serve the writes very quickly because it can buffer them in its DRAM, and the reads more slowly because it actually has to go to flash media. And we need to combat this and instead make our own decisions about which request it will serve next. This is not terribly important in a pure read or pure write workload, but even a write workload here also mixes several different workloads. We have the Memtable flush, we have the commit log, and we have compaction, and we want to control the relative bandwidth. And we do that by throttling I/O in user space and forming a queue there and having an algorithm select the next write or read to go into the actual disk. So next, let's look at the Memtable flush. Oops, I see it's folded. So let's look at the bandwidth again. We see it ramping up rather quickly. So the Memtable flush bandwidth has to match the commit log write in this sort of saturating workload. Otherwise, you run out of memory to store new writes, and you have to stop serving requests. So we have a controller that adjusts the relative shares between commit log and Memtable, and also all of the other processes, so that we can close the loop and have the Memtable flush keep up with commit log. And we have the same ratio between bandwidth and IOPS because we use the same 128 kilobytes write size. So that was the Memtable flush. Let's take a look at the query. These are the reads. So at the beginning of the workload, there are no reads, but later we have the read bandwidth. It's ramping up as the loader gets up to speed. It's a Java loader, so it takes a bit to warm up, and it reaches about 50 megabytes per second, and then it drops down. And this is because the cache gets warmed up, so more reads are served from cache and fewer from disk. And we can see it keeps relatively steady afterwards. If you perform the division where you divide the bandwidth by IOPS, you will see that the average read size is 10 kilobytes. This is due to the record size. So let's move on to compaction. And looking at the bandwidth, we can see that compaction begins at 0 bandwidth because in the beginning there are too few files to compact. And later the bandwidth is very low, but it keeps increasing. So the database becomes more worried as it sees more and more files being deposited, and it wants to make sure that if and when a read workload starts, it will not have a huge number of files to read. So it increases the bandwidth allocated to compaction. eventually, the bandwidth allocated for compaction can match or even exceed the bandwidth allocated for writes, because the database is trying to make sure that the file layout doesn't get away from it. So here the write workload ended. So immediately the compaction bandwidth, this is both read and write, ramped up. So it's about 150 megabytes per shard, or 300 megabytes per second total. So it's compacting like crazy in order to prepare for the read workload. It wasn't quite complete. So once the read workload started, it again immediately squelched compaction to a relatively low rate. For some reason, the two different shards didn't make exactly the same decisions. This can happen. And in the end, the read workload terminated, and the compaction picked up again and compacted as fast as they can until it ended up with a fully compacted database. So this demonstrates how the database dynamically adjusts to different workloads. And this is a relatively simple workload, but if you have different read and different write workloads concurrently, then this is important in order to keep serving them while doing the background workloads of compaction and Memtable flush. And also you can have streaming workloads where you're moving data from node to node in order to expand or shrink the cluster. Let's move on to CPU. Let's start with the statement scheduling group, which is equivalent to the query. This is processing the CQRL statement and inserting into Memtable or reading from Memtable and cache. And we can see that for this workload, the writes do not consume a lot of CPU, but the reads are able to, the reads do saturate the CPU. So we have writes being blocked by disk and reads being blocked by CPU. Let's look at the Memtable flush. So again, it's consuming a very small amount of CPU, so just 4% of CPU. It's not a very CPU-intensive process with this large record size. With a more typical record size, it can consume a lot more CPU. But for this one, it's relatively easy. The interesting bit here is the shares. So this is the result of the controller trying to make Memtable flushes keep up with the commit log. So it dynamically adjusts the number of shares, and the reference value to compare to is the 1,000 shares that the statement group has. And this applies both to CPU and to I/O. So if it sees that the compaction, that the Memtable flushes are not keeping up, then the shares will increase. If it sees that Memtable flushes are getting ahead, then it will reduce their shares in order to free up CPU for regular write activity. And the same goes on for compaction, although it's using a different algorithm. So you can see that a much smaller number of shares is allocated. And it's slowly increasing because the number of SS tables is slowly increasing, and the database really wants to get them down. As soon as the write workload is completed, then the number of files starts decreasing and the shares decrease with them. So this is the way to dynamically adjust the resources devoted to background processes in order to be prepared for changing workloads. Let's move on to one more dashboard and to see it from a high-level point of view. So here we see the aggregated CPU load. As we can see, the overall CPU used by all of the processes is quite low during the write. It's disk-bound and reaches 100% during the write process. You can also see different number of requests served. So because it's serving more requests from cache, then it became CPU bound, while the writes are necessarily IO bound. So the Gaussian distribution that I used was quite narrow, so quite a lot of reads hit from cache. Let's move on and look at the cache. So here we can see the cache hit and miss rate. Reads with no misses are cache hits. The awkward terminology is because you can have a select statement that reads multiple records, and some of them hit cache and some of them miss cache, and reads with no misses means like a full hit. The entire query was satisfied from cache. So this is relatively constant, while the misses start high, but very quickly the cache gets warm. You would expect there to be an inverse relationship, but I guess it's hard to see because the scales are different. So we have about 12,000 hits per second from each shard, while the number of misses is just 3,000. So somehow it got squelched out. So that's it. There's a wealth more of information, but the video is already long. If you want more, you can find it on the CyllaDB website. There's a lot of material on it. I hope it was enjoyable. Thanks, everyone. Bye-bye.